Okay, so far we've shown that transformations and feature space transformations have an effect that they change this definition of distance and the definition of dot product. And if we change the dot product, then essentially what we're doing is a feature space transformation. What we've shown earlier is that using a transformation like this one that we used earlier, phi of x is equal to x1, x2, and square root of 2, x1, x2 is equivalent to changing the definition of dot product from A transpose B to A transpose B squared. Okay, so this is what we call a kernel function, which is a generalized definition of dot product. So remember, all dot products, all they do is they take in two vectors as input and then they generate a scalar, right? So if a function is able to do that, along with some other properties that don't matter right now, we should be able to use any function as long as it takes in a vector and produces a scalar at the output. We can use that as a kernel function. So the dot product definition that we are most familiar with is A transpose B, or the Euclidean dot product. That is called a linear kernel. And if we use a linear kernel, we can do linear classification, as we are just going to see in a minute. We can have other kernels as well. This is called a polynomial kernel. It takes in two vectors, x and y, and takes a dot product of those, adds 1 to that, and raises it to the power d, which is typically an integer power. So d can be squared, so you can have a polynomial kernel of degree 2. You can have other kernel functions as well. Let's say you can have a kernel function, a very famous kernel function is the Rbf kernel function, which is x minus y. You take that, those are the two vectors that you've been given. You subtract them, you compute the distance of those. So this is a norm bit. You square that, so now we have a scalar. You multiply it with a value a. So this is going to be a parameter that you need to set. And then you can take an exponential of it. So that is going to give you a scalar at the output that measures, that gives you a generalized, another definition of the dot product. You can have a variety of different kernel functions. The point is, a kernel function is a function that takes in 2 points, 2 feature vectors as input and generates a scalar. It has a few other properties as well that we're not going to talk about right now. And you can read a text on that. What are the properties that need to be satisfied for it to be a kernel function? But the important bit is to understand that when we use a different kernel rather than the linear kernel, then that corresponds to our transformation in the original feature space, right? So that should allow us to use to be able to give to get linear to use a linear discriminant over a non-linearly separable problem to achieve, hopefully, linear separability between two classes. Okay, so that's the effect of it. It's important to understand the effect of that, which is quite simple. A change from this to, let's say, a change from the linear to the polynomial kernel, like the one that we had over here as well, changes or applies a transformation in the feature space or folds the feature space. Okay, so that's what we are going to do. If we have got, let's say, n examples that are given to us in the training data, we can compute or we can apply the new definition of dot product or the kernel function between all pairs of those. Let's say if we got 3 examples in our training data, then we can construct a kernel matrix, right? Like this one that is shown over here. It's called a gram matrix. And we can compute the kernel value or the dot product of the first example with itself, the first example with the second example, the first example with the third example, and so on. So this is going to be a square matrix of size n by n in general. As long as this matrix is always going to be symmetric, as long as that matrix is symmetric and it's positive semi-definite, and I don't want you to be confused too much, so you can go ahead and read about the definition of positive semi-definite. As long as this kernel matrix satisfies these properties, we have at our hand a valid kernel. So those are the additional requirements for a function to be a valid kernel. But that's not you don't need to understand that in too much detail right now. All you need to understand is that whenever we apply a kernel function, whenever we use a generalized dot product, there is an implicit transformation in the feature space taking place. Okay. However, now what we are going to do is to introduce this concept of kernels because they allow us to do nonlinear separability. We are going to introduce those into our support vector machines. This is what was done by Sholkov in 2001 in a theorem in the late 1990s actually, and he gave us a theorem that is called the Representative Theorem. Okay, and that allows us to introduce the concept of dot products in the SVM. If you think about it, the discriminant function of a support vector machine is W transpose X. So it already has a dot product over here. It's a dot product between the weight vector of the support vector machine and a given example, right? And another thing that we saw in our previous work, in one of our previous lectures, is that this weight vector over here has the same dimensionality as the examples. That's why we can take a dot product, right? So this W vector over here lives in the same feature space as the examples itself. But what Sholkov showed in 2001 or earlier is that you can express this weight vector of a support vector machine or any linear classifier as a linear combination of the examples that you've been given. Let's say if you've been given 4 examples. So let's say if you have these 1, 2, 3, and let's say we have 4 examples over here. Let's say if we got these 4 examples, each one of, we know the feature representation of each one of them, then the weight vector of any support vector machine that we obtain after optimization can be expressed as a linear combination of the weight of the feature vectors of these examples. And that's easy to understand because W has the same dimensionality as X. So it can be expressed, this weight vector can be expressed as a linear combination of these 4 vectors. So these alphas that you see over here control how much contribution each example has on the output W. If alpha, so it's in this case, let's say we got 4 examples, let's label them. This example 1, this is example 2, this is example number 3, and let's just say this is example number 4. Let's say the feature representation of example 1 is 0, 0, this is 1, 0, this example is 1, 1, and this example is 0, 1. Then we've got 4 examples over here. Then what this equation shows is the representative theorem, and what that means is we can write the weight vector of the support vector machine in the following form. We get alpha 1 and we multiply it with 0, 0. We add it to alpha 2 times the second example, 1, 0. We add it to alpha 3, which is 1, 1, and we add alpha 4 times 0, 1. So that is going to give us a 2-dimensional vector, which is W1 and W2, right? So it is going to give us these 2 values. And this is what the representative theorem states, that if you have, and we're not going to go into the proof of that, but what it says is that since the weight vector of a support vector machine or a perceptron or any other linear classifier or machine learning model lives in the same feature dimensionality or the same feature space as is spanned by its examples, that means that weight vector can be expressed in terms of the the feature values of the original example. Well, while we were developing a support vector machine earlier, we wanted to find out what alpha was or what W was, right? So what was this weight vector? We wanted to find a weight vector that could separate the examples with a line, right? Now, what this representative theorem says is that an alternate way of formulating the same problem is that instead of finding W, we are interested in finding these alphas, right? And if I find those alphas, then we essentially have a weight vector at our hands, and then we'll be able to do classification, right? So this is the new thing that we need to introduce. Please pause this video and try to understand this. Understanding this theorem is important based in order to understand what we are going to do next. So to put it simply, if you have got a bunch of examples, your weight vector of the support vector machine can be expressed as a linear combination with weights alpha of those examples. since we don't know what the optimal weight vector is for a support vector machine, and we find that out through optimization, we can either do that by searching for W directly, that is what we had been doing earlier, or we can alternatively use an optimization procedure to find these values of alpha for each of these given examples. And that is equivalent, both of those problems are equivalent. And that's what we're going to show over here. If we look at the decision function of a support vector machine, then that can be written as f of x is equal to w transpose x plus b. Let's just rearrange it. And since we know that w is nothing but the linear combination of the given examples, so we can write alpha j into xj, right? So if we use, this is coming from the representative theorem that we just talked about. So this is representative theorem, right? And if we use that, then what that allows us to do is we can plug it in over here. And if we do that, this is what we get. So we get P, which remains the same over here. And then we get J is equal to 1 to N, alpha J, xj transpose, because W is being transposed, multiplied by X. So f of X is now expressed in B plus J is equal to 1 to N, alpha J, X transpose J. And this is what we wanted. We wanted to express, we wanted to have a dot product here when we were talking about X. And this dot product is only based on the data that we have. So we already have these n examples. And what this allows us to do is we can write a discriminant function of X of the linear discriminant in terms of these alphas now, which we need to find out. But we now have a dot product over here. And based on our discussion earlier, if we replace this dot product with a generalized dot product called a kernel function, then that means we'll be doing implicit transformations, which will allow us to solve non-linearly separable problems. And that's what we are going to do over here. So instead of having xj transpose x dot product, we will replace this with kxj into x, which is the generalized dot product. And this is what is called the kernel trick, so or kernelization. So what we've done so far is we have used the representative theorem to replace W with dot products of a given example X with the examples that we know. Okay, so xj comma x. And we have these coefficients called alphas that we still need to work on. We need to find those. We also have in the support vector machine, there are two parts, right? If we look in the formulation of the support vector machine, there is f of x, which we have now expressed in terms of in terms of a kernel function over here, already done. And the other bit is yi, we know that. We know what 1 is, we know what 0 is, we know what max is. So we pretty much sorted out everything in this bit. On the left-hand side, we have got W transpose W because, and that's what we still need to change, or we still need to kernelize that. But we know that W, based on the representative theorem, we know that we can express W in terms of the given data points. So we can write W transpose W like this. So we get, this is the first W, this is the second W, and if we combine this, we can write it like this. Okay, so we get summation over, so we get a double summation for one going over I from 1 to n, and other going from j is equal to 1 to n, and then we get alpha I, alpha j into k xi xj. So that is how this bit is being kernelized using the representative theorem. So essentially, what this allows us to do is we can have this SVM formulation, and we use this representative theorem over here to get a new representation of the same support vector machine. But the good thing about this support vector machine formulation on the right-hand side is that it is now kernelized. We have kernel functions over here, right? That means if I use k a b is equal to a transpose b, it's the same exact thing as the original formulation. But if I change the definition of this dot product to, let's say, a transpose b square, and then if I solve this optimization problem now, What I'm doing is I'm doing an implicit transformation of each of my data points into a different feature space in the hopes that we'll be able to achieve linear separability in that space, just like we have seen. So kernelization, or this kernelized SVM, that is this one, is more generalized in comparison to the original formulation that we have. They are mathematically both equivalent, but they have a different way of representing this dot product, and we can change the definition of the dot product in this right one, whereas in the left bit we'll need to do the explicit transformation of x in order to achieve linear separability. So that is the primary difference between kernelized and non-kernelized support vector machines. Okay, so I hope you've been able to understand this. Please understand the steps or the mathematics. It's a very simple trick based on a theorem which is called the Representative Theorem by Sholkov, that allows us to express a support vector machine in terms of dot products. And based on our previous discussion, if we change the definition of dot products, we can make it really generalized, and we'll be able to solve linearly non-separable problems. Okay. So in this formulation, if you take a look over here, there are some really interesting things to note. And this is coming out as a consequence of this representative theorem. Okay, the first thing is there is no mention of any dot or any w here. No w. You cannot see any w. Okay, so the weight vector is not present in this formulation, the kernelized SVM formulation. We know kxi xj for all training data points, because we know xi, we know xj, we know what the kernel function we want. Let's say if we want kxi xj equal to xi transpose xj, we know that what kernel function to apply, right? So we know all of this, okay? And all of the dot products have been replaced with generalized dot products. So we can actually use any dot product function that we want, or any kernel function we want. We can use xi xj squared, xi xj is equal to xi transpose xj squared, or any other function that I've shown you previously. And then that is going to allow us to solve linearly non-separable problems as well. So we know xi, we know xj, that means we know kxi xj, we know this bit. The only things we don't know are alphas. We don't know what the value of alphas should be. So instead of this minimization now being with respect to w, this minimization is with respect to alpha and with respect to b. Okay. And let's say if you solve this optimization problem by magic, let's say if you got an optimizer in which we plug in this function, we plug in all of the data, and it spits out all the values of alpha, then we've essentially solved the problem, right? So we can solve this using gradient descent if you want to, but this time the gradient descent is not going to be with respect to w, but will be putting the gradient descent with respect to alphas, and we'll be solving for that. Once we obtain those alphas that give us the minima of this optimization problem, we will have a solution to the support vector machine. So once we get alphas, we will be able to calculate the decision function value of a given point. We have already all the data points that we've been given. We have those. We plug in those, and we can calculate what the function value of that is going to be. Okay, so pretty neat. And that allows us to generate linearly non-separable boundaries, and that's what I'm going to show you next in this demo. Okay, so let me open this up. So far what we've covered, while it's opening, I can give you a summary. So it can be really confusing if you're going through this for the first time. I understand that, but if you go through it once more, it's going to be really easy. What we wanted to do is we wanted to solve linearly non-separable problems, and we saw that if we change the definition of dot products, we should be able to do that. However, the support vector machine didn't have any dot products of the examples with themselves, or the example with a new test example. But the representative theorem allows us to rewrite this formulation, and once we have done that, we obtain the values. We can obtain a kernelized SVM, so we can change the definition of dot product to achieve implicit feature transformations. Okay, so this simple demo of support vector machines allows us to use different kernels. So if we can, if you look through the help of this link, and I already provided you this link, you can actually use different types of kernels here. So let's say we want to use this CS support vector classifier. So we'll be specifying S to be 0, which it is already by default. So we don't need to make any changes. And then we can specify a kernel type. So the kernel we want to use is the linear kernel first. So or the classical dot product definition. So we use key is equal to 0, and then we take these points, we make 3 points, and we can take a different color. And if I run it with a value of c equal to 100, then this is the boundary that we get. We've already obtained that, so this is pretty good classification. But if I use the same kernel, a linear kernel, and if I have I'm sorry, let me clear that. If I have a linearly non-separable problem, like this one, this is the exclusive OR problem. And if I try to run this, it won't solve the classification problem perfectly, as you can see. This is a linear discriminant obtained by using this value of C with a linear kernel, and as you can see, this has not separated the two classes. There are still misclassification errors over here. We can overcome this by changing the definition of the dot product. Instead of having a dot product A transpose B, or in this case U transpose B, we can change it to a polynomial kernel, and we can specify this gamma. We can specify U. We already have U and V, and we can specify this coef 0, and we can specify the degree, right? And to do that, we first need to set t is equal to 1. Okay, so that is going to be a polynomial kernel. Then we can set a degree value. So we want to change the degree to 2. We want to use A transpose B squared as our kernel. So remember, that is equivalent to the transformation that we've talked about. If we do that, this is going to be equivalent to that. And then we can set the G value, which is this gamma value over here, to 1. So that's what we're going to do. And if we run this, oh, we probably need to increase the value of C. Oh, we've been able to make 2 cuts, right? Just like the one that we started off with when we were folding the paper, right? So I welcome you to try different kernels and try to understand this support vector machine concept in a bit more detail as we go through this lecture. So you can try with different kernels with this link. It's a very, very helpful applet that I'm very grateful to whoever made this, and it really helps us understand the concept of support vector machines. So when we are working with support vector machines, we've got features, okay, and we need to choose a value of C, and then what we need to do is to pick a value of kernel. We need to pick a kernel that can be a linear kernel if the problem we think that is linearly separable, or we can also pick a non-linear kernel, just like a polynomial kernel, and we can make non-linear classification boundaries. This is the same thing done in Python. So instead of importing a linear support vector classifier, sklearn also has a support vector classifier, which allows you to use the concept of kernels. So we have got a data point. So using the support vector machine is really easy. You're given a bunch of data points, 0, 0, 0, 1, 1, 0, and 1, 1. We have got the corresponding labels. You can classify, you can pass what kernel we want to use. Let's say we want to use the polynomial kernel. If you want to use it with degree is equal to 1, so it's going to be the dot product kernel. You can specify with this value of C, and then you can obtain a solution for it, and it will give you a boundary like this. You're welcome to try out this code. It's part of the exercise that I've already given you. But we know that this will not be able to, this classifier will not, this kernel, linear kernel, will not be able to satisfy or solve the problem of when we have this exclusive OR problem, which is linearly non-separable. And all we need to do when using this sklearn is to change the definition of kernel from linear to polynomial, and we need to specify degree is equal to 2. And if we do that, then we can see that we get this decision boundary in which the two classes have been neatly separated now. Okay. So to understand this in a bit more detail, I welcome you to read this tutorial, as well as I'll be posting some links in the book on how to use the support vector machine, but using it is much easier than it's a bit tricky to understand the concepts behind the kernel function. But if you have a good intuitive understanding of how that relates to paper folding, you should be fine. So if you if you're failing in understanding this concept from scratch, begin uh, with that paper folding experiment that we saw, and try to understand how changing the definition of dot product is equivalent to folding. Then the next step to understand is how does the representative theorem allow us to express a support vector machine or kernelize a support vector machine so that we end up with these dot products, and we need those dot products there so that we can change those dot products to arbitrary functions to achieve linearly, to use this discriminant function, linear discriminant, to solve linearly non-separable problems. Okay, so this is the steps you need to do in order to classify or to use these support vector machines in practice. You need to prepare the pattern matrix, that is, for each example, obtain a set of features. You pick a kernel function to use. You pick the parameter of the kernel functions. For example, if you what degree to use for the polynomial kernel, or if you're using a radial basis function kernel, what are the parameters that you want to use there? And you need to pick a value of C. There are the support vector machine library within sklearn gives you some default values, which you should change to and play with those to understand the concept of C, that role of different kernels. And once you do that, your library is going to execute the code, and it's going to give you the values of those alphas that determine your discriminant function. And once you have that and you have the original training data set, you can use that to classify unseen data. Okay, so that's the pretty good thing about it. And the strength of the support vector machine is that it's optimal. It gives you an optimal boundary. Its margin is maximized, and it can be kernelized. That means it can solve linearly non-separable problems. However, training is relatively easy. There's a single optima, so you cannot go wrong in optimization. So it's going to converge, unlike neural networks, as we shall see. And it scales well to very high dimensional data, even if you have thousands of features. Because the margin is being maximized, it's going to perform quite well in high dimension spaces. And the only critical point of support vector machines is that you need to pick a good kernel function. Now, there are kernel functions that guarantee linear separability no matter how bad your data is structured. So, for example, the radial basis function allows you to do that. But in order to understand that, I would welcome you, if this is your first exposure to support vector machine, I would welcome you to try with different kernels and try to visualize them and to understand this concept in a bit more detail. Okay? Now, one of the questions I typically ask students in class is, why is it called a support vector machine? And that is something that I want you to think about. Why is a support vector machine called a support vector machine? Well, where does the name come from? Okay, and we are going to discuss that in a later lecture. Okay, so today what we have covered is support vector machines. We have seen how we can use these uh, to get optimal separation boundaries for linearly non-separable data sets. Okay, there's a lab exercise on that, and I welcome you to play with that. Okay, thank you.